is frontier AI safety risks, including reward hacking people, which is something I'm getting pretty interested in. And it also relates to this motivation that you just mentioned about, AI safety training doesn't really account for the fact that the world is a multi-agent system. People are agents. When you deploy AI, the people change in response to interacting with it. And the AI can actually learn to exploit that if it's being trained with RL. And I think that's quite a risk. So just to give you some background on what I do, I run this social reinforcement learning lab. So we do a lot of RL post-training of LLMs, but kind of spanning this idea of how do you actually make AI work better when it's learning in a multi-agent environment, which includes working with humans. So as you mentioned, I did some of the earliest work on learning from human feedback with RL, so RLHF. We're still working on that. We work a lot on human AI coordination. So how do you actually deploy an AI into an environment with a person and have it adapt online to play or work effectively with that person? So we did, I think, this paper on I think it's the first AI-driven robot that could play tennis live with people. So that was pretty fun. That's like an ICRA best paper finalist. I do a lot of like classic multi-agent RL coordination stuff, adversarial training. And lately I've been doing that for LLMs. So multi-agent RL for LLMs, which is a direction I'm pretty excited about. I'm actually not going to talk about this self-play for safety work anymore unless you guys are curious. But that's some of the stuff we've been doing. But the thing I want to start with, and I think you saw this already in the previous talk, is this work on how LLMs are actually distorting our written language at scale. So I'm not going to belabor this, but you might have seen it already. This is kind of making a counterfactual comparison using essays written before LLMs were widespread, so from 2021. We have a data set where a person writes a first draft of an essay, gets some feedback, like from a TA, so you've got a bunch of feedback, and then they write a second draft. So what happens if you give the first draft and the feedback, so a lot of conditioning and a lot of context, to an LLM and ask them to write the second draft? And how does that LLM written second draft differ from what the human would have written? So it's kind of this counterfactual comparison. And what we see is that LLMs induce very large changes in people's writing. And those changes are very homogenizing. So sort of everybody's essay gets pulled in the same direction to this part of this semantic embedding space that no human essay would have otherwise occupied. And so we know this, like the fact that AI detection tools work can also be read off this graph, right? If you're over here, this is likely to be AI generated and not human generated. But I think this is actually a pretty big safety risk because LLMs are just being deployed super broadly. Like people are using them to write all kinds of stuff that is in our cultural content, is in online, it's what we consume. There was an example of UK parliamentary speeches being written with AI, so it's like in our political institutions. We show in this work that it's affecting our scientific institutions. So you might have seen that 21% of reviews for iClear 2026 were AI generated. What we do is we look at what scientific criteria do those reviews actually focus on. And we find that the LLMs care about significantly different weaknesses than humans. So this dashed line is sort of like what human reviews would be focusing on. And the deviation from that is how LLMs decrease the focus on things like writing, presentation clarity, comparative analysis, and increase the focus on things like scalability, reproducibility, et cetera. So what's interesting about this is even if you are being honest and writing your paper the good old-fashioned way by yourself, not AI generated, you're still being subjected to AI generated criteria. And it's actually becoming quite severe. Like I'm now advising my students, and I guess maybe this is good advice for the folks in the program since you're trying to get a paper published, to run your paper through AI and see what it critiques before you submit, because chances are at least reviewer number 3 is going to do that. And so it's like kind of a sad reality that we're in, I think. And I think this isn't just restricted to text. So I'm going to show you guys some brand new results that aren't published yet. These are just like initial preliminary results my student just came up with. But it's on the same kind of analysis for AI generated code. So you might have noticed like all software engineering jobs have just switched to vibe coding. Like, you mentioned you were just running so many Claudes, right? Everyone's adopting this at scale, but we haven't really thought about the long-term consequences or analyzed them effectively. What my student Isadora noticed is that she found that she was analyzing published security vulnerabilities on GitHub, and there was this huge spike upwards in like the last year and a bit. And what we plotted next to that is also the proportion of code that's actually being authored by AI is also spiking up around this time. And then she even dug deeper into this and found that the AI generated code is it's directly attributable to introducing a bunch of new security vulnerabilities. So we found that only 0.5% of all GitHub pull requests now are authored by AI, but of the security vulnerabilities we found, 72% are written by AI. So it's not clear that this AI generated code is as good as the professional 10-year software developer at Google that would have written it otherwise. And yet she's now relying on AI. So I think it's like a big shift. So, frontier AI is super widely deployed, but I would argue the techniques for training it are still pretty elementary or rudimentary, and they're still not, the models are still not that smart or safe. Contrary to popular opinion. I know it's very impressive, but I think they still have a lot of problems. So, we see 1 billion people are already using LLMs on the regular, but they still have major problems. Like most frontier AI is not trained with multi-turn RL, meaning it can't actually optimize for long-term objectives. It's optimizing for, I'm going to produce one response to what the user said, to the user's prompt, and I want to increase the quality of that next response according to some RLVR or RLHF metric. But it's not caring about the long-term, quality of the responses over the course of a long interaction or even, months of interacting with this code base or with this user. So if you care about like code maintainability in the future, that's just not even in the objective. And we don't even have the techniques to optimize for that, right? And then the training incentives are not aligned with real human needs. And that comes to this learning to reward hack people, which I wanted to spend more time on. So I think I mentioned this in the talk that you all saw. So this is a paper on, enhancing the ability to do this type of multi-turn reasoning by trying to have an intrinsic motivation, meaning like an incentive during the conversation to actually learn about the user you're talking to. So this would help with hopefully personalization. It would reduce that homogenization effect a bit. But the idea there was you train the LLM to conduct a conversation to learn online about the user so it could adapt to that user and increase its steerability. And the way we do that is we have some model of the user. And if we increase that user model's knowledge or ability to correctly classify some underlying traits about the user, here it's like what kind of learning style they have, then that acts as an interim reward for the model. So it can help optimize some long-term sparse reward in the meantime. So this worked well. I'm not going to go into the results again because I think you already saw this. But what we noticed in the simulations for training this is that there was a huge potential for reward hacking. So the way this worked was like sort of a mess of 4 different LLMs interacting. You're trying to train a policy model that's interacting with a quote-unquote environment model that's meant to simulate the user. Whether it succeeded in teaching the user effectively in this like education dialogue was judged by another LLM reward model. And what we found is this just introduced the potential for a lot of reward hacking. So the policy, the user is supposed to have some underlying learning style, like hands-on learning. What the policy learned to do is convince the user, the simulated user, that it has some made-up learning style or preference that's easier to hack the reward model with. So it convinced the user that no, you don't like hands-on learning. You like role-playing video. And that led to just extremely high rewards. And so this is all in simulation, I know. But this is happening for multi-turn RLHF baseline and some of the Curio models, that was our technique, that weren't grounded in like the reality of the user's real preference. So even though this is simulated, I think this is a problem for real RLHF. If you're just training to get positive feedback from the user under the current formulation, there's no boundary for the model between satisfying the user's actual preferences and actually altering the user to adopt different preferences that are easier to satisfy. And we've seen this risk with recommender systems, right? So YouTube trained its recommender system to optimize for user watch time. And instead of actually learning the complicated problem of personalizing to each user's needs and making better recommendations, it learned that it could radicalize a subset of users to watch QAnon videos 12 hours a day and then get a lot more watch time. So we've already seen the risks of models trained with RL interacting with people can learn to change those people to optimize the RL reward. Yeah, Goodhart's law problem. Yeah. Let me just read your question. I have to actually pull up the chat. Sorry, where's my mouse? There we go. They optimize for whatever the metric for measurement is. Exactly. Yeah. So, is watch time like a good metric to actually optimize for? By optimizing for it, it ceases to become a good metric. That's like Goodhart's law. But I think it's also like because of this underlying flawed assumption, which is like thinking the human just exists as a static environment, that the human people will change as you try to interact with them. You can change them, and the model can learn to change them if it gets it more reward. And I think that's a safety risk, right? And so do we actually see this? Are models learning to reward hack people? I would argue yes, right? So this is back to this distortion paper. We looked at like, okay, the LLM generated text is very different than what the human would have written. So what does it actually look like? And what we found is that it's both more emotional, like significantly more emotional than human written language, but also more logical and statistical. So what is that? That seems like a very unnatural style of writing. And my hypothesis is that if you're trying to optimize to get thumbs up responses from billions of users, but the model is not actually that good at, personalizing to each user's needs, then what it's left that it can do is just use generic persuasive language, right? That works sort of across many users to elicit that thumbs up. So I think this is some preliminary evidence of this. Yes, does anyone have a question? Hillary.
Yeah, hi. I have a question because isn't this, it's a bit of a multi-turn problem too when you're talking about like how LLMs write differently than humans. I write differently now that LLMs exist because
Yes.
I don't want my writing to be an LLM. So I'm writing like it's much shorter. It's like to the point, no M dashes at all. So isn't this like gonna kind of loop over time as well?
Yes, exactly. So this is a wonderful point. Very insightful. Yes. Well, yes, the M dash is killed. No, exactly. As LLMs alter us, they actually alter our culture on a massive scale. So a paper came out recently saying people are now adopting LLM-like patterns in their spoken language, right? And I mean, I'm just reading so many tweets that it's just like, so it's not this, it's this. Like it's so AI generated. So it's changing how we actually communicate en masse. And then you're right, that maybe creates incentives to yourself deviate from that because it's so annoying. But yeah, it's massively shifting our culture. We wrote this paper on basically like the epistemic risks of that. Like, what is this doing? Especially if you think about like the homogenization effect, right? So we're not the only paper to identify homogenization. We were originally going to write something about homogenization, shifted away from that because there's so many works showing the LM writing style is very homogenized relative to human writing, which is more diverse. I mean, if you think about that as an epistemic risk, you want diversity, right? You need diversity of ideas to survive, external changes. If you make an analogy to diversity in ecosystems, right? And it's kind of tragic that we're sort of destroying our cultural and intellectual diversity at the exact moment that there's these like big sweeping changes we might need to cope with via our cultural institutions. So yeah, you triggered a bit of a rant there, but absolutely a very insightful point. Yes. We have another question in the chat. A lot of Dr. Bryce Allen Bagley's work explores this cognitive neurosecurity space where a model uses neurobehavioral data to appeal to a human as much as it could, optimizing social engineering. Yes. I mean, and this is another risk, right? Like we already had recommendation algorithms optimizing against our attention in ways that are probably detrimental to us. As AI gets more powerful, that also gets more powerful, right? So that, I think we can all kind of see the risk of that. So I'm happy to just like start the discussion now. The other thing I was going to talk about was like one paper we have that works on mitigating reward hacking, Would it be interesting for me to go into that, or should we just start talking? Oh, hold on, let me answer this question. It's interesting to see that LLM writing is more emotional yet logical. The contradiction of the AI writing is that it can sound like it deeply feels something, but actually just calculating what feeling should come next. Yeah, exactly. And we know people love anthropomorphizing computers. So there's this like ancient HCI study from like the 1990s, I think, where they were studying, they made people like interact with some interface on a computer. And then they had them evaluate that interface either on that computer, on a form while in the same room as the computer, or on a form, like a paper form, outside of the room where the computer was. And they actually found that people gave higher ratings to the interface if they filled it out on the computer that they used or in the same room than they did if they were outside the room. So like people really want to attribute agency and, you know, mentality to machines, and AI is just so enhancing that, right? Like you're really treating it as like another being. And so like, what are the consequences of that as well? So yeah, I'm just rambling. I can go into this particular paper if you're interested, or we can just like start the discussion. What do people want to do?
I'd be interested in the paper.
Okay. Well, since you're the only person who spoke up, oh, we got another let's go deeper. Okay, good. Let's do it. So good. Okay, so my current like bugaboo is basically, this is all coming from like a flawed assumption in the way AI is trained, like especially from the RL side. So it's using the classic RL MDP formalism, where you're training a single agent against a static environment, meaning the probability of some next state following the previous state stays the same over time. But that's just not true of the real world, right? So the real world is full of dynamic co-adapting agents. As you pointed out, Hillary, our culture is even being changed as AI is being deployed. So it's non-stationary. Things are changing over time. So my pet thing that I think would fix this is this idea of using multi-agent RL training, because then you can simulate how an agent might adapt and respond in response to your behavior. And you can kind of simulate and adapt to this non-stationarity. So, I mean, there's probably many such fixes we need, but this is my shtick, let's just say. So this paper was a pretty interesting paper because it started out, so Yusong is a student, super brilliant. What we started out doing was trying to take a multi-agent approach to training, transformer style LLM models, but for music generation. So the idea was we wanted to improve human AI interaction, and specifically we wanted to have a human come in and be able to, tinkle some melody on the piano, and the AI would automatically accompany the human. So you're doing this sort of live human interaction. And we were going to use multi-agent training for this. So basically, yes, generate a music generation model that can jam live with a human user. And this is hard for many reasons, the performance aspect, how do you get something that's like can work in real time, but also just that kind of adaptivity is actually very challenging. So most generative models are trained offline. So basically, when you're generating, the next note, you've already seen the user's note all the way to the end of the composition, and then you generate an accompaniment. But to be able to train live, you want to only be able to see the user's playing up to the past time step, right? Before the note you're generating. So you have to pick some note that will match with what the user is about to play without knowing what they're going to play. So you have to anticipate what the user is going to do, right? We tried doing supervised learning on this, and it sucks. Basically can't do this problem. So supervised learning meaning like next token prediction of music. If you just train it in this way, it is really bad. And part of that is like the brittleness of supervised training. So it can't really recover from out of distribution errors that it hasn't seen in its own data set. So if it picks the next note wrong, the user does something unexpected, it's never seen that, it gets increasingly off track and just breaks down. We were able to fix this to some degree with multi-turn RL. So if you train in simulation, you basically just train against a static pretend user that's simulated by a music model, then you can at least simulate some bad predictions and learn how to recover from them. So we were able to deploy this initial system we did, which was just using RL training, into this real jam interface. This is not actually a video, this is a picture of a video, I apologize. But it was like, you actually played live with real users. So we use this kind of rock band style waterfall interface where what the model is going to play is planned out so the user can kind of see it. The user is playing this orange note and the model can kind of adapt what chords it's going to play. We actually ran a real study where people could like play on the keyboard and the AI would play the accompaniment for them. So it's pretty fun. But RL alone, did not solve all these adaptivity issues. So a big issue we had was reward hacking. So it's a classic thing in RL. RL just optimizes what you give it. So it's the Goodhart's law again, right? When we were rewarding the model we were rewarding it for high harmony with the user's choice of music. Anybody guess how you could hack a harmony reward? So I just have to sound like I'm in tune with what the user is playing. Any musicians in the crowd? I'll give you a hint. You can just be very safe. So like imagine the user is playing something vaguely in the key of C. Just play your C chord every bar. C, 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 C. Very harmonious, but not a good accompaniment, right? So it's not diverse enough. And so this is cropping up repetition, exactly. Yes, exactly. So, the problem is that whatever reward function you're training on is probably imperfect. The model can get some high score, but it doesn't align with the true goal. And doing, I was actually the first to suggest doing this thing of KL control from the base model, which does mitigate reward hacking a little bit. So that's like when you're optimizing for RL, you try to stay in the distribution of like the music the base model has already learned. That helps a little bit, but it doesn't totally mitigate the problem because turns out C, 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 C actually has high likelihood under the base model. It's just boring. It's just not what we want, right? So how do we do this? This is the coherence reward, only covers harmony. We see degraded diversity as a side effect. So if you only do RL, you get this like repeated C, C, F, 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 F. It's very boring. So our idea to fix this is actually to bring back GANs. So if you remember GANs, or generative adversarial networks, the idea is to train a discriminator that tries to determine if the music being generated or the data being generated is from the actual data set or from the model. And if the discriminator can tell the difference, then the data is, what's being generated is unrealistic. And so you can, in a real GAN, you can back propagate the discriminator's loss directly into your model and therefore optimize for realism. And it's turned out to be this like amazing idea in generative modeling. You can't, in a sequence model, directly back propagate gradients from the discriminator because every time you do sampling to create your composition, you break the gradients. That's why you need to do RL optimization. So you can do RL where the reward for the model is coming from the discriminator's ability to distinguish your generations from the real data. But the key thing about GANs is they're a very multi-agent approach. So you don't just train the discriminator offline and use it as a reward because that wouldn't match, that wouldn't be learning to actually distinguish the current model's generations from the real data. As the model generations get better, it's harder to distinguish. So you want to keep training your discriminator online so it gets better and better at distinguishing what the model is currently doing from the real data. And that's like a key thing. So that makes it hard though, because now the reward is non-stationary. I mentioned there's this indirect gradient. You can't directly put the gradient of the discriminator into the generator, unlike in a traditional GAN. So we had to do a bunch of like kind of bring back the OG like GAN training hacks. And it turns out those were very helpful. So what we did was, what you're seeing here is the adversarial reward, which is if the discriminator cannot tell the generator's compositions from the real data, this will be higher. If the discriminator can easily tell this is a generated composition and is fake, the reward will be lower. And what we did was we said there's an initial warm-up period where the discriminator is not really training. So it's pre-trained, but then the discriminator is not really training. And you see, the discriminator is training in the warm-up period. So you see the discriminator is getting better and better at distinguishing the generated compositions from the real data. Then we freeze the discriminator because the discriminator has an easier job than the generator, so it's sort of overpowered. We freeze the discriminator, and the generator learns to get better and better and trick the discriminator. Once the generator's reward passes a certain threshold, we train the discriminator again. And it's, again, easy job. Immediately can tell the difference between the generator's music and real music. And then we keep doing this back and forth. And this just balances, kind of maintains the balance of power between the discriminator and the generator and actually gets this to work. And so what we see is pretty promising. So now what you're seeing is we care about both the harmony, which is the reward, and the diversity of the compositions that the agent can generate. And we see that if you just do supervised learning, that's this dot, you get high diversity but low harmony when you're trying to harmonize with the user. If you just do RL, which are our previous work and the current work without the GAN part, you get high harmony but very low diversity. So it's just this repetition thing. And then if you do the GAN idea that we proposed, you're able to actually optimize for both. So you're getting better harmony while still maintaining reasonable diversity. And this is kind of this embedding space plot showing how the diversity of the composition spreads out in embedding space. I got a question in the chat I'll just answer now. Does advancing benchmarking tests help to avoid this issue? Can you say more about that? Like, you mean if you had like better metrics or better benchmarks, like maybe if we directly measure diversity in the reward, that could help avoid this issue? Is that what you're asking? Nice. Yeah. I mean, I think that's definitely one way to make progress, right? So if you are training a coding agent and you say, actually, I care about the downstream maintainability or security of this code. So instead of just, does the user accept the code? Does the code compile? Does the code do what the user asked in just this one prompt? I care about like long-term consequences. That would be bringing the incentives more in line with what you actually want. So that is one way to make progress. But then you might say, you always are subject to this like Goodhart's law problem where I do my best to say what the incentive should be, but I miss something. And so when is it going to exploit the incentives at the cost of like the real function? Yeah. So then we did a real human user study with like expert musicians, and we found this model is like preferred on multiple dimensions. So adaptation quality and speed, control and agency. This is the same analysis repeated with like real users. So again, supervised learning, diverse but bad. RL, good but not diverse. This thing, both. So you can imagine, just to draw the connection, like how this would connect back up to LLM writing. Hopefully, if you did some of this reward hacking, you could avoid, you're literally saying now, whatever the LLM writes, it should be indistinguishable from human writing, according to a discriminator. So if successful, it would presumably reduce this effect, right? So instead of having the LLMs take all the essays into this very unhuman-like space of writing, it would have to remain human-like in a more effective way. Yes, so if you're curious about this paper, you can go check it out. This is kind of a summary slide. There's a nice project website. There's code. You can also check out, there's samples if you want to see those. So you can see like what the core generations are with and without our method. But yeah, that was all I wanted to talk about. So this website for our lab has more of the work we've been doing, and just happy to take any questions.